Hello, BC Calculus students. This is Mr. Johnson, and this is the start of section 8.7. We've already done the investigation for the polynomials, and we've done a little bit of practice here. So some of this is going to feel like review and is going to be repetitive from that, but there is some good practice in here, especially with multiple choice problems, and we will get into then the free response questions. And in every case, there's a little bit of an iteration of the type of question being asked. And so we'll just continue to build the concept. So from the investigation and the practice up to this point, remember we have a Taylor polynomial centered at a, or in other words, any value, 0 or otherwise, in the form of f of a plus f prime of a multiplied by x minus a to the first plus f double prime of a times x minus a to the second and divided by 2 factorial and so on. And you can start to see the pattern form, and that's what we studied in the investigation, and that's what we've been working on up to this point. The general term is going to be the nth derivative at a of x minus a to the n divided by n factorial. And again, this is the general Taylor series expansion for the power series, and we could use this for any function that we wanted. So for example, we should have cosine of x memorized at this point, for example. We could generate it from this general form. We could generate cosine of x, we could generate e to the x, we could generate the one that we discussed way early on in section 8.2 where we talked about 1 over 1 minus x. We also talked about how if you have a series centered exactly at 0, that is a Taylor series, but more specifically you could call it a Maclaurin series. And the formation of that one is just simply an a value of 0, so you have f of 0, and then you have f prime of 0 times x plus f double prime of 0 times x squared divided by 2 factorial, and so on. You can see that it's just the same as the one we wrote above in red, except this time you're just evaluating at 0, and so it looks a little bit simpler, and this is definitely more common. All right, let's talk about e to the x. Now, we've discussed it as a class, but just as a quick review, if you were to think about generating this, and we're gonna do a center of 0 for this one. So if we were to use that blue form above, we have f of 0, which is let's start with f of x. So we have f of x, which is of course e to the x, and f of 0 then would be 1. We have f prime of x, which is of course e to the x, and the derivative at 0 is 1. You could continue this process because remember the derivative of e to the x is e to the x. So no matter what, any level of differentiation is going to be evaluated at 0 will be 1. And so therefore, when we come up with our general form for e to the x for the Maclaurin series centered at 0, we have e to the x equal to 1 plus x squared divided by 2 factorial, excuse me, plus x cubed divided by 3 factorial, and so on. It's very similar to the series for 1 over 1 minus x, so be really careful with it. The general term is x to the n over n factorial. This has a radius of convergence of infinity and an interval from negative infinity to infinity. So in other words, this power series is perfectly aligned to e to the x forever, which is amazing. Now let's say we want to come up with the Taylor series for e to the x, but centered at 2. So that means that, again, our function is e to the x. That means that evaluated at 2 would be e squared. That means that our derivative, of course, is e to the x. Evaluated at 2 is e squared, and so on. You can see the pattern. So if you were to use your general form for the Taylor written in red at the top here, we're just using f of a would be f of 2. That would be e squared. F prime of a, that would be f prime of 2. That would be e squared, and so on. And so our form for this particular series expansion for e to the x, now centered at 2, is going to be e squared plus e squared times x minus 2 plus e squared times x minus 2 squared divided by 2 factorial plus e squared times x minus 2 cubed divided by 3 factorial, and so on. The general term would be e to the n. times, not e to the n, e squared times x minus 2 to the n divided by n factorial. So again, you can see that, generally we're going to center this at 0, but you could certainly center it elsewhere, and that would be fine. You would be able to figure out how to expand it based on our two general forms, which again are at the top of this page. So just keep in mind that those two are going to lead you to many, many functions and be able to organize their series expansion. Let's go to the next page. Okay, for example 3, we're going to look at sine of x. Now again, we've discussed this. We've also discussed cosine of x. So for example 4, this was during the investigation, so I'm not going to repeat that. So during the Taylor investigation, and so for cosine of x, we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. And we just, basically with that investigation, we took the time to generate this and look at the patterns. And so I'm not going to redo that. You can look back on that video. But this particular series expansion, to me, is easier to remember if you think of cosine as an even function. So if cosine's even, you can notice the pattern of the exponents is also even. So that helps us sort of memorize that. But if you think about the relationship between cosine and sine, if we were to take the derivative of each one of these, the derivative of cosine is negative sine, and the derivative of 1 is, of course, 0. The derivative of the next term would be 2x divided by 2 factorial. The next derivative would be 4x cubed over 4 factorial minus 6x to the 5th over 6 factorial, and then so on, okay? Now, we want, obviously, sine, not negative sine. So if we were to then just multiply by negative 1 across, we would have sine of x equal to, and then let's simplify. So for example, 2 divided by 2 factorial is 1. 4 divided by 4 factorial is 3 factorial. And so you're simplifying as well as multiplying by negative 1. And what we have then left over is x minus x cubed over 3 factorial minus x to the 5th over 5 factorial. And we could even just add in the next element, I think, because we can start to see the pattern here. I'm going to go ahead and write the general term that we tend to use. There's a couple ways you can represent it, of course, but it's an odd power. And again, think back to the pattern. Cosine is even, so the powers are even. Sine is odd, so the powers are odd. And so it might help you memorize it, I suppose. With cosine of x, the interval is infinite, so it's negative infinity to infinity, and the same with sines. So as we compare these two and as we generate them, they're perfect matches from the function to the power series. Okay, let's go ahead and skip 4 because I mentioned we did that at the investigation. Let's do the Maclaurin series for f of x, which is equal to x cosine of x. And remember, you can algebraically manipulate a lot of this. And we have cosine hopefully memorized. If not, go ahead and memorize that as quickly as you can. And so when we think about cosine of x, and we're simply just multiplying by x to get our function f of x. So f of x, which is x cosine of x, means that I take each of the terms and I multiply by x, giving me the following power series. Our general term will be negative 1 to the n, x to the 2n plus 1 divided by 2n, that quantity factorial. And then, of course, we would continue in terms of our pattern. So there you go. You can see that we can start manipulating these different functions now. We can start using the things we know, and then we can algebraically manipulate it to get to a different function. Let's move on to the next page and do a summary. So here's our summary. It's important to keep organized here and to understand each of the ones that we need to have memorized. So for e to the x, we have 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial, and so on, x to the n over n factorial. For sine of x, we have we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, x to the 7th over 7 factorial, and then so on. Remember, sine is odd, So that's one way to help memorize it. Okay, with cosine, that one is going to be even, so we're going to start with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And then the one that we learned at the very beginning of all of this, the geometric one, is 1 plus x squared plus x cubed. It probably seems so simple now, I suppose. And then we have x to the n. The general Maclaurin is centered at 0, of course. And so we have f of 0 plus f prime of 0 times x plus f double prime of 0, times x squared divided by 2 factorial plus x triprime of 0 times x cubed over 3 factorial, and so on. Our general term would be the nth derivative at 0, x to the n over n factorial. And then the general Taylor, centered anywhere. In this case, we'll just center it at a, so it's f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 factorial, f triple prime of a times x minus a cubed divided by 3 factorial, and so on. This one's a little longer, so we have the nth derivative at a of x minus a to the n over n factorial, and there we go. Okay, so here's our list of 6. Basically, you have to know these. You absolutely have to know these. As we start to look at these, keep in mind that we have an interval of convergence for e to the x, which is negative infinity to infinity. So that's going to be your interval. We'll call it I. The radius is infinite. That is true for both sine and cosine. So we have an infinite interval. In other words, it's perfectly aligned, which is just amazing to think about. So we have the interval for each of those and the radius. For our geometric one, remember the interval is very small. It's from -1 to 1, and the radius is, of course, 1. Okay, so those are the interval and the radius for those 4. For the general Maclaurin, the general Taylor, remember the way we find each of those is going to vary based on our function, and we're using the ratio test. So the ratio test will allow us to figure out what is the interval and radius of convergence. Okay, that is it for the first video. In the next handful of videos, we'll go through some practice and some iterations of how this looks on the actual AP exam. Thank you.